So in this video we're going to look at topic 1.5, which is symbols, formula and equations. Essentially this topic is all about forming balanced symbol equations and how we do that. So the topic will go through a few examples of how we actually construct these balanced symbol equations. There's also be a few questions for you to have a go at yourself, and for that you're going to need to have a periodic table handy. But in terms of the background to this topic, so understanding how we're going to get these balanced symbol equations ourselves, we need to look at, first of all, at formula and how we form them. So whenever we're talking about chemical formula, all we mean is we want a symbol version of something we would normally say in words to make it a bit easier to see what's going on. And the way we get the chemical formula will depend on the type of substance we want the formula of, in terms of whether it's an element or a compound. So if we look first of all at how we get the chemical formula of elements, there's kind of two options for how you might do that. Now, most of the elements in the periodic table, if you ever have to give the chemical formula of that element in an equation, all you will do is just look at the periodic table and see what symbol is written beside that element. So for example, if we're having to look up the formula of potassium, so we need to look at the periodic table, find wherever the word potassium is written, and we'll see that this is here. Look at the symbol, which is K, so the symbol for potassium would just be a K. Another quick example, if we're trying to find carbon, so we look at the periodic table, find the word carbon, and our formula or symbol for carbon will just be a capital C. Now that will be the case for most of the elements in the periodic table, but there's a few exceptions. Some elements are what we know as, or what we call diatomic elements. And diatomic elements always come as pairs. So if we're ever giving the chemical formula of a diatomic element, we also have to give a little 2 beside it to show that they're coming as batches of 2. Now the diatomic elements are as listed on the screen. So the ones you need to know about are iodine, hydrogen, nitrogen, bromine, oxygen, chlorine and fluorine. Might seem a little bit difficult to remember these ones are different, so there's kind of like a phrase that you can learn off. I have no bright or clever friends is how I always remember it. So to show you what that means in terms of formula, it's basically the same as what you did for these elements. You have to look up their symbol in the periodic table, but you need to put a little 2 beside it. For example, for iodine, the symbol for iodine is I, but because iodine is an example of a diatomic element, which means 2 atoms covalently bonded together, we have to give the formula as I with a little 2, because there's 2 iodine atoms joined together. And that'll be the same for all of these elements, as we've shown here. So that's how you would find the formula of an element which might be appearing in the chemical equation. Now when you look at the compounds, and again, like we had 2 different ways of working out formulas of elements, there's kind of 2 main categories of working out formulas of compounds. The first batch is what we might call the common compounds. And the common compounds are a list of chemical compounds that your exam board expects you to know off by heart for the exam. Now that sounds like a lot to ask of you, but do bear in mind that lots of these compounds come up in quite a lot of detail in certain topics throughout the year, so you kind of come across them quite a lot anyway. But the full list that you're meant to know for the exam is as follows. So it does look like quite a long list, but I'll talk you through it here. What I've done is I've underlined in red the ones which are most common for what comes up in your year 11 exam. So water being H2O should be quite familiar to you. Carbon dioxide, CO2, is quite important. Ammonia being NH3. Then your acids and alkalis, hydrochloric acid HCl, sulfuric acid HSO4, nitric acid HNO3, sodium hydroxide NaOH, and potassium hydroxide KOH. So these ones, it is important you know the formula is carbon monoxide, sulfur dioxide, nitrogen monoxide, nitrogen dioxide. Technically speaking could come up, but much less likely to come up in a year 11 exam. So that's the list of compounds you're just kind of meant to know. So if it comes up in a word equation, you have to make it into a symbol equation. They would expect you to know, for example, that carbon dioxide's formula is CO2 without you having to work it out yourself. Now, obviously that's only a few compounds, and there's lots of compounds which could come up in chemical equations. We might call those, as opposed to common compounds, uncommon compounds. So when you get to an uncommon compound in an equation, you would have to work out the formula of it yourself. Now there's a technique we would use to work out the formula of a non-known compound, and it's known as the swap and drop. Now it's easiest to see how we use the swap and drop if we look at a few examples. So for example, if I was given the compound sodium chloride, I might have to work out the formula of sodium chloride is. So here are my steps. I look at the 2 elements within the equation. So sodium is an element and chloride is an element like chlorine, and I write down their symbols. So look up the periodic table, sodium symbol is Na, and chlorine symbol is Cl. The next step is that I have to work out what charge would be on these elements when they form a compound with each other, an ionic compound with each other. Now the easiest way to do that is to look at the group number. So sodium is in group 1, so it's got 1 electron in the outer shell, therefore it will lose 1 electron to form an ion. Its ion will be 1+. So group 1 equals a 1+ ion. Chlorine is found all the way in group 7. It's got 7 electrons in the outer shell, therefore it needs to gain 1 electron to get to the outer shell, like the noble gases, therefore it will have a 1- charge as an ion. What I do with the swap and drop is that I look at the numbers associated with the charges, so 1+, 1-. I take those numbers, I know you wouldn't normally write one in, but I'm going to do in this case. Take the numbers, swap them over, and drop them down. And what that would give you basically is Na1 Cl1. Now obviously if you've just got one of something in chemistry, you don't need to say you've got one of it, you just write it once. So the formula of NaCl would just be, or formula of sodium chloride would be just NaCl. Another example, if we were given magnesium chloride, I would do exactly the same process. I would write down the symbols of the two elements involved, so magnesium and chlorine. Step 2, I need to work out what charges would be on their ions. So magnesium is found in group 2, need to lose 2 electrons to get further shell, which means it's 2+ charge. And chlorine, like we had before, is in group 7, needs to gain 1 electron to get further outer shell, it'd be a 1- charge. Take those two numbers, swap them over and drop them down. So therefore the 2 is now at the bottom of the chlorine, the 1 is now at the bottom of the magnesium, Mg1Cl2. And remember, we don't normally put a 1 in, so the final formula of magnesium chloride is just MgCl2. One final example, which is a little bit harder, would be copper sulfate. Now copper sulfate is a little bit more tricky for a couple of reasons. First of all, you've got copper, Cu, and you've also got sulfate. Now sulfate isn't an element, it's what's known as a molecular ion, which means it's part of a compound, an ionic compound which contains more than one element. So if you see a word which clearly isn't from an element, so sulfate is not the same as sulfide, you look in the back of the periodic table and check there, and you should find it. So you see sulfate here, it says SO4 2-, so I would write down SO4 2- for sulfate. Coming back to copper, we need to give its charge. The problem you find with copper is it's actually in the middle of the periodic table. It's in the transition metals. Therefore, you haven't got a group number to help you out find out what the charge is. So if you find an element in a swap and drop which isn't in the group, it's in the transition metals, you should look at the back of the periodic table and you will see copper written here. It says copper 2+. So that's what you use for your swap and drop. Now we've got 2 + 2-, so we're going to swap that over and drop it down. And you end up with Cu2SO4 2. So after brackets around the SO4 because saying they've got 2 of the whole thing. But in this case, because you got the same number on both things in the formula, you kind of cancel down a little bit like fractions in maths. So this becomes CuSO4. So that's a couple of examples of how you might form uncommon formula for uncommon compounds using a technique called the swap and drop. So having looked at how we form different chemical formula, let's look at how we actually fit those into chemical equations. So most of the work you have to do with chemical equations is to actually practice forming chemical equations, but we're going to give a little overview of the main kind of key points behind chemical equations here. First thing is the parts of the equation you should recognise. If we look at an example, here's a simple chemical equation between magnesium and oxygen to form magnesium oxide. The bits on the reaction before the arrow are known as the reactants because they are reacting together. The things you form on the right hand side after the arrow are called the products because they're the things you are producing in the reaction. You could be asked for 2 different types of equation in an exam. The first type would be a word equation. Now a word equation is kind of what you expect. You just have to describe the reaction using your words. The key thing is you can't put any formula into a word equation. That sounds obvious, but it's very easy. For example, if you have a reaction that produces carbon dioxide, to write down CO2 instead of carbon dioxide, because that's a very common way of saying carbon dioxide is CO2. You're not allowed to do that in a word equation. You must write the full words carbon dioxide. The other type of equation you might have to look at is a symbol equation. And in a symbol equation, you would take a word equation and convert all of those words into actual formula, which is what we've looked at in the first part of the video. A key thing about symbol equations is that they must be balanced. In other words, you must have the same number of each element on each side of the arrow. Another thing which might come into a symbol equation is that occasionally will ask you for state symbols. Now they won't always, and I always make it very clear if they do want state symbols. In a state symbol, you're just describing whether each substance in the equation is either a solid, liquid, gas, or is found in aqueous solution, which means dissolved in water. So how you show that is with a little symbol in brackets you put after each formula. A solid is shown by S, liquid by L, gas by G, and an aqueous solution is shown by AQ. So to put this all together into practice, let's have a little look at going through 5 examples of symbol equations you might have to do in your Year 11 exam. So the first reaction is one that you come across in the periodic table topic, where sodium reacts with water to make sodium hydroxide plus hydrogen. So we're imagining here that the question is asking us for a balanced symbol equation version of this reaction. So my general starting point is, even if it doesn't require a word equation, I always write out the word equation first, even in the margin or the bottom of the page. And what I'm trying to do is converting all the words into their proper formula and then balancing it at the end. So if I work through this example, the first word is sodium. Sodium is an element. So what I've looked at before is that most elements, if you're trying to find the formula, you just take it off the periodic table. Sodium is not found in the list of diatomic ones, so it's fine, just go off the periodic table. If I look up sodium, I find Na beside sodium. The next thing in the equation is water. Now water is a compound, but it does come into our list of common compounds. We're just meant to know the formula off by heart, therefore it's H2O. The next thing I come to is sodium hydroxide. So sodium hydroxide is what I would consider also another common compound. So it's in our list of ones we're meant to know. So NaOH, so it's going to fit in after the arrow. And finally, hydrogen is another element. We have to be careful with hydrogen because it's found in our list of diatomic elements, so it has to go in as H2. So that's every word converted into a symbol. The last step is I need to make sure it's a balanced symbol equation. So I need to basically count up every element on each side. So I've got one sodium, that's balanced. I've got one oxygen and one oxygen, that's balanced. However, I've got 2 hydrogens here and 3 hydrogens here. Now to get that balance maybe is a little bit tricky. When I'm balancing an equation, I can't change any of the formula. I can only use big numbers in front of the formula, big balancing numbers. If I put a 2 here, that looks like a bad move, but what I've basically got now is 4 hydrogens on the right hand side. So 2 hydrogens here, 2 hydrogens here, which makes it easy to balance it on this side. Because we put big 2 there, that's 2 2's, which is 4 hydrogens here. My hydrogens are now balanced. That's also rebalanced the oxygens, because I've got 2 on this side and 2 on this side. To get the sodium's balanced, however, I just need to put a final big 2 in front of here. Our second reaction is also an example of a reaction you find in the periodic table topic. This is a halogen displacement reaction. So again, you can pause the video here and have a go with it yourself, but I'm just going to look through and show you how to construct it. First one, chlorine is an element. From our list, it's also a diatomic element, so let's go in as Cl2. Potassium iodide is a compound, but it's not a common compound. Therefore, we have to do a swap and drop to work out what the formula is. Potassium symbol is K, iodine symbol is I. Potassium is found in group 1, therefore it must have a plus charge, 1 plus. Iodine is found in group 7, therefore it must have a minus charge, 1 minus. If I swap and drop 1 and 1 with each other, they'll basically just get 1 of each, which gives a final formula of Ki for potassium iodide. Potassium chloride, similar kind of strategy. It's not a common compound, therefore I need to do a swap and drop. Potassium is found in group 1, therefore it's a 1 plus charge like before. Chlorine is also found in group 7, therefore it's got 1 minus charge like iodine did. Swap and drop 1 and 1 with each other, just gets 1 of each, so I get KCl. And finally, iodine is I, but it is in our list of diatomic elements, so it has to have a little 2 beside it. So to get the equation balanced, if I notice I've got 2 chlorines here, but only 1 chlorine here, I therefore would have 2 in front of this KCl. I have 1 iodine here, but 2 over here, so I need another 2 in front of this, and that gets 2 Ki. And if I look, that actually has balanced out potassium as well. I've still got the same number on each side, 2 here and 2 here. The third example is a reaction that you come across within the acids topic, such reaction of a metal with an acid to make a salt plus hydrogen. So we go through the process again. Again, pause it if you want to have a go yourself first. Magnesium is an element, but it's not a diatomic element, therefore it can just go down off the periodic table as Mg. Hydrochloric acid is what we consider a common compound from a list of ones we're meant to know off by heart. Its formula is HCl. Magnesium chloride is not what I would consider a common compound, therefore I have to do a swap and drop to work out its formula. Magnesium is found in group 2, therefore it's Mg2 plus in the swap and drop. Chlorine is found in group 7, therefore it's Cl minus in the swap and drop. Swap the big numbers over, the charges over. I therefore get 1 magnesium, because there's 1 minus for the chlorine. I get 2 chlorines because there's 2 plus on the magnesiums, gives me MgCl2. Final thing in the equation is hydrogen. We've seen it before. Hydrogen is just H, but it's a diatomic element, therefore we have to have H2. Balancing the equation, if I look here, I've got 1 chlorine here, but 2 chlorines over here. I've got 1 H over here and 2 H's over here. Therefore, if I put a big 2 in front of HCl, I'll have the correct number of hydrogens and the correct number of chlorines, as well as the correct number of magnesiums on each side. The final example we look at is another reaction from the acids topic, this reaction of a metal carbonate with an acid to make a salt plus water plus carbon dioxide. So let's go through the process again. Again, pause it if you want to go yourself first. Copper carbonate is not what I would really consider a common compound, therefore I have to use swap and drop to find it. Copper is Cu, but it's one of those funny ones which isn't in a group, it's in the transition metals. Therefore, if I look in the back of my periodic table, it tells me it's copper 2+. Carbonate is another example of something in a formula which isn't actually an element by itself. If I check in the back of the periodic table, I see carbonate as CO3 with a 2- charge. If I swap and drop the numbers there, I get 2 of each, but remember that can cancel down to 1 of each. So the formula of copper carbonate is therefore CuCO3. Sulfuric acid is what's considered a common compound, you're meant to know. Its formula is H2SO4. Copper sulfate is another uncommon compound, therefore I need to work out its formula by swap and drop. Copper, like we had before, is Cu2+ of the back of the periodic table. Sulfate again isn't an element, therefore it's on the back of the periodic table as well. It's SO4 with a 2- charge. Going to swap and drop again, and I get 2 of each, which cancels down to 1 of each, which gets me CuSO4. Water is a common compound, it's H2O, and carbon dioxide is also a common compound, it's CO2. Looking at the balancing here, I've got 1 copper and 1 copper. I've got 1 carbon and 1 carbon. I've got 7 oxygens on this side. I've also got 7 oxygens on this side. And I've got 2 hydrogens here, 2 hydrogens here, 1 sulfur here, 1 sulfur here. It's actually balanced already, even though it looks like quite a long equation. One final type of equation just look at very quickly that occasionally comes up in year 11 exams is what's known as half equations. In a half equation, you're just taking a full equation, but you only are interested in how one element behaves over the course of the equation. So that's easier to see in an example. If I take one of the reactions we've looked at already, the question might say, give the half equation for magnesium in this reaction. So what that means is I'm only interested in wherever magnesium appears in the equation, and don't want to show anything else. So if I kind of look at what happens start to finish, it starts off Mg, and it looks like its ending is Mg, but however, if you think about this came from a swap and drop. What we did to get MgCl2 is we took Mg2+ and Cl- and swapped and dropped to get MgCl2. So if I go backwards and look at what I had at the start, it was Mg2+. So magnesium is turning into Mg2+ over the course of this reaction. To get that balanced, I need to add electrons because magnesium turns into magnesium 2+ because it loses 2 electrons. If it loses 2 electrons, I will show those electrons on the right hand side. 2E-. The way I check if it's on the right side is that the charges should be balanced on each side. So there's no charge on the left hand side. 2+ and 2- together means there's no charge as well on the right hand side.